The Sun is enormous. 1.3 million Earths could fit inside it. Its diameter is 1.39 million kilometers. Light leaving its surface takes 8 minutes to reach us, travelling at 299,792 kilometers per second the entire way. If you stood at the Sun's equator and tried to walk around it, the journey would take you over 100 years without stopping. By any human measure, the Sun is incomprehensibly large. And there is a star out there compared to which the Sun is barely a pixel. A star so large that if you placed it where our Sun sits, its surface would extend out past the orbit of Jupiter. Mercury, Venus, Earth, Mars, the asteroid belt, all of it swallowed, not figuratively, physically inside the star. That star exists. It has been measured. It has a name. Tonight we are going to build up to it slowly, because the only way the number means anything is if you understand what you are comparing it against first. We will start with what stars actually are, then move through scale after scale until the true size of the largest known star in the universe becomes, if not intuitive, at least real. If you have this on because the night is long, stay. This is one of those stories where the actual scientific reality outpaces anything fiction would dare invent. Let us start with the basics. A star is a sphere of plasma held together by its own gravity, generating energy through nuclear fusion at its core. Hydrogen nuclei fuse into helium, releasing energy in the process. The same physics, in essence, that powers a hydrogen bomb, except continuous, controlled by gravity, and sustained for billions of years. The size of a star is determined primarily by its mass and by what stage of its life it is in. More massive stars are not simply scaled-up versions of smaller ones. They live faster, burn hotter, and eventually swell to enormous proportions as they exhaust the hydrogen fuel in their cores and begin fusing heavier elements in shells around an increasingly dense core. This swelling phase, the red giant, or for the most massive stars, the red supergiant or hypergiant phase, is where the truly staggering sizes occur. Our Sun, currently a fairly ordinary main sequence star, will itself eventually swell into a red giant in roughly 5 billion years, growing large enough to engulf Mercury and Venus and possibly reach the orbit of Earth. But our Sun is a modest star. To understand the largest stars in the universe, we need to look at stars vastly more massive than the Sun. Stars that begin their lives already dozens of times more massive, and that swell to proportions the Sun will never approach. Let's establish a scale we can hold on to. The astronomical unit, the average distance from Earth to the Sun, is about 150 million kilometers. This is the basic yardstick of our solar system. Mercury orbits at 0.39 astronomical units, Venus at 0.72 astronomical units, Earth, by definition, at 1 astronomical unit, Mars at 1.52 astronomical units. The asteroid belt sits roughly between 2.2 and 3.2 astronomical units. Jupiter orbits at 5.2 astronomical units. Now hold that number, 5.2 astronomical units, the distance to Jupiter, in your mind. It will matter very soon. Let's talk about how astronomers actually measure the size of a star that is thousands of light years away and that, in most cases, cannot be resolved into anything more than a point of light, even through the most powerful telescopes. There are several methods, and they reinforce each other. The first is interferometry. By combining light from multiple telescopes separated by some distance, astronomers can achieve angular resolution far beyond what any single telescope could manage, effectively synthesizing a telescope with an aperture as large as the separation between the individual instruments. For a handful of the largest, closest stars, this technique has allowed astronomers to directly resolve the star's disk and measure its angular diameter. Combined with a known distance, angular diameter converts directly into physical size. The second is the use of luminosity and temperature combined with the Stefan-Boltzmann law. Every star radiates energy according to its surface temperature and surface area. Hotter stars radiate more energy per unit area, but a star's total luminosity depends on both temperature and size. If you know how bright a star actually is, its luminosity derived from its measured brightness and known distance, and you know its temperature from its spectrum, you can solve for its radius using the relationship that luminosity equals a constant times the radius squared times the temperature to the fourth power. This is the primary method used for most of the largest stars in the universe, because most of them are too far away and too obscured by interstellar dust for direct interferometric measurement. It is powerful, but it carries real uncertainty, particularly because distance measurements to stars thousands of light years away carry their own error margins, and because these massive evolved stars are often shrouded in dust they themselves have shed, complicating the determination of their true luminosity. This is worth holding on to, because when we get to the largest stars in the universe, you'll see size estimates that come with significant ranges rather than single, precise numbers. Not because the stars are poorly studied, but because measuring something this large at a distance this great is genuinely difficult, even with the best instruments available. Now, before we go to the absolute largest known star, let's build intuition with some stars that are merely extremely large, stars that would already, on their own, demolish any human intuition about what a star is supposed to be. Betelgeuse. The bright reddish star marking the shoulder of Orion, visible to the naked eye in winter skies across most of the world. It is a red supergiant, roughly 700 light-years away, though recent measurements have refined this distance with some disagreement among studies, ranging from about 530 to 660 light-years. Betelgeuse's radius is estimated at somewhere between 750 and 1,000 times the radius of the Sun, depending on the specific measurement and model used. This star is known to pulsate, changing size somewhat over time, which is part of why pinning down an exact figure is difficult. Using a working estimate of around 900 solar radii, if Betelgeuse replaced our Sun, its surface would extend out past the orbit of Mars, and depending on the specific size estimate used in a given study, potentially out toward the asteroid belt or beyond. Sit with that for a moment. A single star, large enough that Mercury, Venus, Earth and Mars would all orbit inside it, inside the stellar material itself, not in some empty cavity, but submerged in tenuous outer stellar atmosphere. Betelgeuse is currently in the late stages of its life and is expected to explode as a supernova, astronomically speaking, soon, though in human terms this could mean any time in the next 100,000 years, an interval astronomers consider essentially imminent. But Betelgeuse, as enormous as it is not even close to the largest star known. Let's go further. VY Canis Majoris. For many years, VY Canis Majoris held something close to the title of largest known star, and it remains one of the most studied hypergiants in the sky. It's located roughly 3,800 to 5,000 light-years away in the constellation Canis Major. Estimates of its radius have varied considerably over different studies, ranging from around 1,400 solar radii up to figures as high as 2,000 solar radii in earlier estimates, with more recent and more careful analyses tending to converge somewhere in the range of 1,400 solar radii. At even the more conservative end of these estimates, If Vy Canis Majoris replaced the Sun, its surface would extend well past the orbit of Jupiter and approach the orbit of Saturn. This is a star whose volume, if you calculated it directly from its radius, would be large enough to contain literally billions of objects the size of our Sun. Vy Canis Majoris is also surrounded by an enormous nebula of material it has shed over its lifetime. Arcs and loops of gas and dust extending out for light years, evidence of the violent and unstable mass loss that characterizes the final stages of a hypergiant's life. Now we arrive at the star that, by most current measurements, holds the title of the largest known star in the observable universe, Uy Scuti. Let's talk about it properly. Uy Scuti is a red hypergiant located in the constellation Scutum, roughly 9,500 light-years from Earth. Some estimates place it slightly closer or farther, in the range of 9,000 to 9,800 light-years, again reflecting the inherent difficulty of pinning down precise distances to objects this far away. The radius estimates for Uy Scuti have varied across different studies. This is important context because you'll sometimes see headlines citing wildly different numbers, and the reason is genuine scientific uncertainty rather than sloppiness. Early estimates from around 2012 placed Uy Scuti's radius at approximately 1,700 times that of the Sun, a figure that, when it was published, briefly made Uy Scuti the most extreme estimate among known stars. More recent and refined analyses, incorporating updated distance measurements and more careful luminosity calculations, have revised this figure somewhat, with several modern studies converging on a radius in the range of roughly 750 to 1,700 solar radii, depending on the specific assumptions and data used, with values around 1,000 to 1,300 solar radii appearing frequently in more conservative recent literature. Let's work with the headline figure that made Uy Scuti famous, and that remains within the plausible range according to multiple studies, approximately 1,700 solar radii, while keeping in mind that this represents the upper end of current estimates rather than a single settled value. At 1,700 times the radius of the Sun, Uy Scuti's diameter would be approximately 2.4 billion kilometers. Let's translate that into the terms we established earlier. The distance from the Sun to Jupiter is about 778 million kilometers, 5.2 astronomical units. Uy Scuti's diameter at this estimate is more than 3 times that distance. If you placed Uy Scuti at the center of our solar system, replacing the Sun, its surface would extend beyond the orbit of Jupiter, past Mercury, past Venus, past Earth, past Mars, past the entire asteroid belt, past Jupiter itself, and out into the space between Jupiter and Saturn. Mercury, Venus, Earth, Mars, the asteroid belt, and Jupiter would all exist inside the volume of this single star. To put the scale of this in terms of light travel, light takes about 8 minutes to cross from the Sun to Earth. Light would take over 2.5 hours to cross the diameter of Uy Scuti alone, meaning that if you were standing at the surface of this star, light leaving one side would take more than 2.5 hours just to reach the opposite side of the star itself, never mind leaving it. Let's talk about volume, because volume scales with the cube of radius, and this is where the numbers become genuinely difficult to hold in your head. If Uy Scuti has a radius approximately 1,700 times that of the Sun, its volume would be approximately 1,700 cubed times the volume of the Sun, roughly 5 billion times the volume of the Sun. 5 billion suns could fit inside the volume of UY Scuti by this estimate. The Sun itself already contains about 1.3 million Earths by volume. So the volume comparison to Earth becomes a number with so many zeros that it stops being intuitively meaningful. Somewhere in the range of several quadrillion Earths could theoretically fit inside UY Scuti by volume, treating it as a simple sphere. These are simplifications, of course. Stars like UY Scuti don't have sharply defined surfaces the way a solid object does. Their outer layers are extremely tenuous, fading gradually into the surrounding interstellar medium, and the radius being measured is typically defined by where the star's atmosphere reaches a certain optical depth, the point at which it becomes opaque enough that we consider it the visible surface. So, in a strict physical sense, UY Scuti doesn't have a hard edge the way a planet does. But even accounting for this nuance, the scale remains almost incomprehensible. Let's pause and consider something important about why a star can be this large in the first place. Because the physics is worth understanding, not just the scale. UY Scuti is classified as a red hypergiant. It is in an extremely advanced and unstable stage of stellar evolution. Its estimated mass is actually relatively modest by stellar standards, somewhere in the range of 7 to 10 solar masses, far less massive than many other supergiants and hypergiants, some of which have masses dozens of times that of the Sun. This is a crucial point that often surprises people. UY Scuti's enormous physical size does not correspond to enormous mass. It is large in volume, but relative to many other massive stars, not particularly massive. Its density, as a result, is extraordinarily low, far lower than the density of air at sea level on Earth. In fact, significantly lower than what we would normally even classify as a meaningful vacuum on Earth, though still vastly denser than true interstellar space. This makes sense once you understand the physics of late-stage stellar evolution. As a massive star exhausts the hydrogen fuel in its core, the core contracts and heats further, while the outer layers of the star, no longer held in equilibrium by the same balance of forces, expand dramatically. The star's luminosity remains very high. UY Scuti's luminosity is estimated at somewhere between 100,000 and 340,000 times that of the Sun, while its surface temperature drops to relatively cool levels for a star, around 3,000 to 3,600 Kelvin, compared to the Sun's roughly 5,800 Kelvin. Because luminosity depends on both temperature and surface area, a star radiating this much energy at a relatively low temperature must have an enormous surface area to account for it. This is precisely why hypergiants like UY Scuti and VY Canis Majoris and Betelgeuse are so large. Their high luminosity combined with their relatively cool surface temperature mathematically requires an enormous radius to produce the observed total energy output. This is the core physics. A hypergiant is, in a sense, a star that is spreading out its tremendous energy output over a vastly larger surface area, which lowers its surface temperature and gives it the characteristic reddish color of these stars, while still radiating an enormous total amount of energy. Let's talk about what's happening inside UY Scuti and what its future likely holds. Stars of this mass and evolutionary stage are not stable in the long term. UY Scuti is in the process of fusing increasingly heavy elements in its core and in shells around its core. Having exhausted hydrogen fusion in its core, it's likely now fusing helium, and, depending on its exact mass and evolutionary trajectory, it may go on to fuse carbon, neon, oxygen, and silicon in successive stages, each stage proceeding faster than the last. This is a star living on borrowed time, astronomically speaking, though borrowed time for a star can still mean hundreds of thousands or millions of years, since stellar timescales are so vastly different from human ones. The eventual fate of a star like Scuti, given its mass, is almost certainly a supernova, a catastrophic explosive death in which the star's core collapses, triggering a shock wave that blows off the outer layers in one of the most energetic events known in the universe, briefly outshining entire galaxies before leaving behind either a neutron star or, depending on the remaining mass, potentially a black hole. When this happens, and it could be tomorrow, or it could be hundreds of thousands of years from now, astronomically speaking, Scuti will, for a brief period, become one of the brightest single objects in the observable sky from Earth, despite being nearly 10,000 light-years away. It's worth noting explicitly, when astronomers say Scuti could explode soon, they are using astronomical timescales. The light we currently observe from Scuti left the star approximately 9,500 years ago. Whatever is happening at Scuti right now, in real time, will not be known to us for thousands of years. For all observational purposes, we are looking at the star as it was when human civilization was first developing agriculture. Let's widen the frame for a moment, because Scuti's status as the largest known star comes with an important caveat that's easy to overlook. The phrase largest known star is doing a lot of work in that sentence. It does not mean the largest star in the universe. It means the largest star we have currently measured and confirmed, among the stars we have been able to study with sufficient precision. The observable universe contains an estimated 2 trillion galaxies, each containing, on average, hundreds of billions of stars. We have detailed size measurements for only a tiny fraction of these, essentially limited to stars within our own galaxy and a handful of nearby galaxies, where individual stars can be resolved or where indirect measurements through luminosity and temperature are reliable enough to trust. This means there is a very real possibility, arguably a near certainty, that stars larger than Scuti exist somewhere in the universe, simply unobserved or unmeasured by us. The title of largest known star is therefore always provisional, always subject to revision as observational techniques improve and as astronomers survey more of the galaxy and beyond. In fact, the history of this specific title illustrates the point well. V.Y. Canis Majoris held the informal title for a number of years before Scuti's size estimates pushed it ahead. Other candidates, including stars like WOHG 64, also a red supergiant, with size estimates in some studies approaching or even exceeding Scuti's, have periodically challenged the ranking, with the specific numbers shifting as measurement techniques and distance calibrations improve. This is healthy scientific uncertainty, not a flaw in the data. It reflects the genuine difficulty of measuring something this enormous, this far away, often shrouded in the very dust and gas the star itself has shed over its lifetime. Let's go back to the human scale for a moment, because I want this number to actually mean something rather than simply wash over you. If you were to shrink the Sun down to the size of a single grain of sand, roughly 1 millimeter, and scale everything else proportionally, Scuti, at 1,700 times the Sun's radius, would be roughly the size of a large beach ball, about 1.5 meters across. A grain of sand next to a beach ball. That is the Sun next to Scuti, and remember, the Sun itself is already 1.3 million times the volume of Earth. Earth, on this same scale where the Sun is a grain of sand, would be a speck far too small to see with the naked eye, smaller than a single bacterium relative to the grain of sand representing the Sun. This is the scale we're discussing, not metaphorically, measured, calculated, published in peer-reviewed astronomical literature, derived from luminosity and temperature data gathered by some of the most sophisticated instruments humanity has built. Let's talk about something that puts UY Scuti's size into an even stranger context: the relationship between a star's physical size and its mass, and why these two properties can diverge so dramatically. In everyday experience, size and mass tend to track together. A bigger boulder weighs more than a smaller one made of the same material. Our intuition, built entirely on solid objects at human scale, expects volume and mass to scale in some predictable, roughly proportional way. Stars break this intuition completely, and hypergiants like UY Scuti break it most dramatically of all. We mentioned that UY Scuti's mass is estimated at somewhere between 7 and 10 solar masses, modest by massive star standards. Compare this to its volume, roughly 5 billion times that of the Sun by some estimates. If you divide mass by volume to get average density, the result is staggering in its emptiness. The average density of UY Scuti has been estimated at somewhere around 0.0000001 grams per cubic centimetre, roughly 1/millionth the density of water, and substantially less dense than Earth's atmosphere at sea level, which sits at about 0.0012 grams per cubic centimetre. To put this another way, the air you are breathing right now, in whatever room you're in, is roughly 1,000 times denser than the average density of this star. A star so large it would swallow Jupiter's orbit. This sounds almost paradoxical until you understand what's actually happening physically. UY Scuti is not a solid, uniformly dense object. Its core, where nuclear fusion is still occurring, is extraordinarily dense and hot, likely tens of thousands of times denser than its outer layers, possibly approaching densities comparable to or exceeding the Sun's own dense core. But the outer envelope of the star, the vast majority of its volume, is an almost impossibly tenuous, sprawling atmosphere of gas, held only loosely by the star's gravity, extending out for hundreds of millions of kilometers in every direction. If you could somehow stand on the surface of UY Scuti, which isn't really meaningful because there's no solid surface to stand on, you wouldn't experience anything like standing on a planet. You'd be inside what's essentially an extremely hot, extremely tenuous cloud of gas, with density decreasing gradually rather than ending abruptly at some boundary. This is part of why measuring the size of stars like UY Scuti is so genuinely difficult, and why the radius estimates vary across studies. Astronomers have to define some specific point in this gradually fading atmosphere as the surface, typically the photosphere, the layer at which the gas becomes opaque enough that we can no longer see through it to the layers beneath. Different methods of defining and measuring this boundary, applied to a star with no sharp physical edge, naturally produce somewhat different numbers. Let's talk now about what would actually happen physically if you tried to bring UY Scuti and a star like our Sun close together. Not as a real scenario, since this would never occur naturally, but as a thought experiment that helps illuminate the relationship between size, mass, and gravity. Despite being vastly larger in volume, UY Scuti's surface gravity is actually weaker than the Sun's. This follows directly from the physics. Surface gravity depends on mass and the square of the radius. Specifically, gravitational acceleration at the surface equals the gravitational constant times mass divided by radius squared. Because UY Scuti's radius is so enormous, even though its mass is several times that of the Sun, the surface gravity works out to a small fraction of the Sun's surface gravity. Estimates suggest UY Scuti's surface gravity might be on the order of 1/1000th of the Sun's. This means that, counterintuitively, despite being a star whose surface, were you somehow able to stand on it, would extend past Jupiter's orbit, the gravitational pull holding its outer atmosphere in place is remarkably weak. This weak surface gravity is actually a major factor in why hypergiants like UY Scuti experience such dramatic and continuous mass loss. Their outer layers are only loosely bound, and stellar winds, radiation pressure, and instabilities in the outer envelope can drive enormous quantities of material off into space. UY Scuti is estimated to be losing mass at an extraordinary rate compared to a star like the Sun. Some estimates suggest mass loss rates many times that of typical red supergiants, contributing to the visible nebula of expelled material that surrounds it, similar to, though somewhat less extensively studied, than the nebula surrounding VY Canis Majoris. This mass loss is, in a real sense, the star slowly unravelling itself, shedding its outer layers into space even before it reaches its final explosive death. The material being shed now, drifting outward into the surrounding interstellar medium, will eventually be incorporated into future generations of stars, planets, and potentially, billions of years from now, into living things, assuming the standard process by which heavy elements forged in stars eventually become the raw material for new solar systems. Let's talk about distance again, but from a slightly different angle, about how the sheer distance to UY Scuti affects not just our ability to study it, but the very nature of what we're observing when we look at it. UY Scuti sits roughly 9,500 light-years from Earth. To put this in context relative to other distances we've discussed, this is more than 2,000 times farther than the nearest star system to our own, Alpha Centauri, at roughly 4.3 light-years. It's more than 1,000 times farther than most of the individually named naked-eye visible stars in our night sky, the vast majority of which lie within a few hundred light-years. Yet 9,500 light-years, while almost incomprehensibly vast by human standards, is actually a relatively modest distance on the scale of our own galaxy. The Milky Way's disk spans roughly 100,000 light-years across, with the galactic center sitting approximately 26,000 light-years from our solar system. UY Scuti, at 9,500 light-years away, is located in the constellation Scutum, which, from our vantage point, sits roughly in the direction of the galactic center, meaning UY Scuti is actually positioned somewhere in the general direction of, though significantly closer to us than, the dense stellar populations near the heart of our galaxy. This means that when we observe UY Scuti, we are looking back in time by 9,500 years. The light reaching our telescopes left the star's surface around 7,500 BCE, before the invention of writing, before the founding of any civilization we have historical records of, during a period archaeologists associate with some of the earliest transitions from hunter-gatherer societies to settled agricultural communities in parts of the Near East. Whatever UY Scuti looks like today, in real time, we have no way of knowing. It's entirely possible, though we have no specific evidence either way, that UY Scuti has already exploded as a supernova at some point in the past 9,500 years, and that the light from that catastrophic event simply hasn't reached us yet. If it exploded, say 5,000 years ago, we wouldn't know for another 4,500 years. This is a genuinely strange thing to sit with. One of the largest objects we know of in the universe, and we are fundamentally unable to know its current state. We are looking at a photograph, in a sense, that is 9,500 years old, of an object whose entire nature, whether it's a hypergiant star, or an expanding supernova remnant, or a neutron star, could have already changed in ways we cannot detect for millennia. Let's pivot to talk about hypergiants more broadly, because UY Scuti, as extraordinary as it is, exists within a broader category of stars that share these extreme characteristics. And understanding the category helps make sense of the individual star. Hypergiants are an extremely rare and short-lived stage of stellar evolution, occurring only in stars that begin their lives with very high mass, typically at least 20 to 40 times the mass of the Sun. Though as we discussed, UY Scuti itself is something of an outlier in this regard, with a relatively modest mass for a star of its physical size, suggesting it began its life somewhat less massive than many other hypergiants, but has, for reasons related to its specific evolutionary path, expanded to an extraordinary radius. These stars are so massive and luminous and live such short lives, typically just a few million years from formation to supernova, compared to the roughly 10 billion year lifespan expected of a star like our Sun, that they are inherently rare. At any given moment, across an entire galaxy containing hundreds of billions of stars, only a small handful are likely to be in this specific hypergiant phase. This rarity is actually significant for understanding why finding and accurately measuring stars like UY Scuti is so difficult and so valuable scientifically. We're not just measuring a large object, we're catching an exceptionally brief, exceptionally unstable phase in the life of an exceptionally rare type of star, and doing so from a distance of thousands of light years, often through significant amounts of obscuring interstellar dust. Other notable hypergiants and extreme supergiants that have been studied alongside UY Scuti include WOHG 64, located in the Large Magellanic Cloud, a satellite galaxy of the Milky Way roughly 160,000 light-years away, with some size estimates placing it in a similar range to UY Scuti, around 1,500 to 2,000 solar radii, though again with significant measurement uncertainty given its much greater distance. There's also Stephenson 2-18, sometimes referred to by other designations, which generated significant attention in some popular science coverage with extremely large radius estimates, figures as high as 2,150 solar radii were cited in some initial reports. However, subsequent and more careful analysis has called these estimates into serious question, with some astronomers suggesting the original calculations contained errors related to distance estimation, and more conservative recent assessments placing its likely size considerably smaller, possibly comparable to or even smaller than UY Scuti and VY Canis Majoris. This is worth mentioning specifically because it illustrates an important point about how scientific knowledge about extreme objects like this actually develops. Initial estimates, sometimes amplified significantly in popular media coverage, get refined, challenged and corrected as more data and more careful analysis become available. The current scientific consensus, as of recent literature, still tends to place UY Scuti among the very largest known stars, generally either at or very near the top of the list, though the exact ranking among the top several candidates remains an active area of study with real uncertainty. Let's return to the human experience of this scale, because I think it's worth dwelling on a bit longer. Earlier we used the comparison of the Sun shrunk to a grain of sand, with UY Scuti becoming a beach ball roughly 1.5 meters across. Let's extend that same scale model a bit further, because it helps make the rest of the solar system and the rest of the galaxy comprehensible in relation to this star. On this scale, Sun as a 1 millimeter grain of sand, Earth would orbit that grain of sand at a distance of about 107 millimeters, roughly the length of your hand. Jupiter would orbit at about 560 millimeters, just over 0.5 meter away. The Scuti beach ball, 1.5 meters in diameter, would extend out to a radius of about 0.75 meters from its center, meaning its surface would reach almost exactly to where Jupiter orbits on this same scale. This is, in miniature, exactly the comparison we made earlier in full scale. Scuti's surface reaching to approximately the orbit of Jupiter if it replaced our Sun. Now, on this same millimeter scale model, how far away would the nearest real star, Alpha Centauri, be? At a real distance of about 4.3 light years, and using the scale where 1 astronomical unit, the Earth-Sun distance, equals about 107 millimeters, Alpha Centauri would sit approximately 29 kilometers away from our grain of sand Sun. 29 kilometers. On a scale where Earth is a speck too small to see and the Sun is a single grain of sand, the nearest other star system is almost 30 kilometers distant. This is roughly the distance across a medium-sized city, or the distance you might drive in 20 to 30 minutes on a highway. And Scuti itself, at a real distance of 9,500 light-years, would be approximately 64,000 kilometers away on this same scale model, more than 1.5 times the circumference of the Earth. This is what we mean when we say that even the largest known star, despite being almost incomprehensibly enormous compared to our Sun, remains an infinitesimally small point lost in the vastness of interstellar distance. The star itself, were we to somehow travel there, would dwarf our entire solar system. But the journey to reach it, even travelling at the speed of light, would take 9,500 years. Let's sit with a different kind of comparison for a moment. Not a thought experiment with scale models, but a direct comparison of what Scuti's existence implies about the energy involved. We mentioned that Scuti's luminosity is estimated at somewhere between roughly 100,000 and 340,000 times that of the Sun. Let's take a middle estimate, around 200,000 solar luminosities, to work with a concrete number. The Sun itself radiates an almost unfathomable amount of energy, approximately 3.8 times 10 to the 26th power watts, continuously every second for billions of years. This is more energy released in a single second than human civilization has produced through all forms of power generation throughout its entire existence, many times over. A star radiating 200,000 times this much energy every second continuously is radiating roughly 7.6 times 10 to the 31st power watts. There is no meaningful everyday comparison for a number like this. It exceeds by a wide margin the total energy output of every other process happening in our entire solar system combined, by many orders of magnitude. It is energy on a scale that, if even a tiny fraction of it were somehow directed at a planet the size of Earth, would be sufficient to sterilize it instantly. Scuti sits at a safe distance from Earth. 9,500 light-years is far enough that even this staggering energy output reaches us only as a faint point of light, barely detectable without sensitive instruments, invisible to the naked eye. But understanding the actual scale of energy being produced helps make sense of why these hypergiant stars, despite their enormous size and consequently low average density, are still fundamentally violent, unstable, extreme physical environments. Places where matter exists under conditions that have no real analogue anywhere on Earth or anywhere else in our solar system. Let's talk now about what lies beyond UY Scuti. Not in terms of even larger stars, since we've discussed the genuine uncertainty there, but in terms of even larger structures in the universe, because this helps place the entire conversation about the largest star into its proper, humbling context. Stars, even the most extreme hypergiants like UY Scuti, are themselves almost vanishingly small compared to the structures that contain them. Our entire solar system, with UY Scuti's surface reaching out to Jupiter's orbit, would still be utterly invisible, a single point of light at best, from the distance of even the nearest other star system, let alone from across the galaxy. The Milky Way galaxy itself, containing UY Scuti, along with an estimated 100 to 400 billion other stars, spans roughly 100,000 light-years in diameter. On the scale where the Sun is a grain of sand, the Milky Way would span a distance of approximately 600,000 kilometers, roughly 1.5 times the distance from Earth to the Moon. And the Milky Way itself is just one galaxy among an estimated 2 trillion in the observable universe, embedded within larger structures of galaxy clusters, superclusters, and the vast cosmic web of filaments and voids that constitutes the large-scale structure of the universe. UY Scuti, the largest known star, the object whose surface would swallow the orbit of Jupiter, is, on the scale of the universe itself, a detail too small to register, a single infinitesimally tiny point of unusual brightness within one galaxy among trillions. This isn't meant to diminish the star or the genuine wonder of its scale relative to anything we can directly experience. If anything, it should deepen it. We are talking about an object so large that it defies ordinary human comprehension. So large that our own solar system would fit entirely within it, with room to spare out to Jupiter's orbit. And that object is itself an almost unimaginably tiny component of a universe so vast that even galaxies, structures containing hundreds of billions of stars each, are themselves just threads in a cosmic web stretching across tens of billions of light years. Let's talk about something specific and often overlooked: the actual process by which UY Scuti was discovered, and how its identity as an extreme object came to be understood. Because the history of this star's observation tells us something about how astronomical knowledge accumulates slowly, through generations of incremental measurement. UY Scuti was first catalogued in 1860 by astronomers at the Bonn Observatory in Germany as part of the Bonner Durchmusterung, a massive stellar survey project that systematically catalogued the positions and brightness of hundreds of thousands of stars visible from the observatory's location, primarily for the purpose of basic astrometric record keeping rather than any specific search for unusual objects. At the time of its cataloguing, nothing about UY Scuti would have stood out as exceptional. It was recorded simply as a variable star, a star whose brightness changes over time, in the constellation Scutum, given a designation within the survey's numbering system. It is worth pausing on this fact. A star this physically enormous, when observed through the telescopes of the mid-19th century, registered as nothing more than an unremarkable point of light, one among hundreds of thousands being catalogued in a methodical, almost bureaucratic survey of the sky. The astronomers doing this work in 1860 had no way of knowing but one of the entries in their catalogue represented one of the largest physical objects that would ever be measured by humanity. This is true of essentially all astronomical discovery of this kind. The scale or significance of an object is almost never apparent at the moment of its initial observation. It takes decades, sometimes over a century, of accumulated technological improvement, refined distance measurements, better spectroscopic instruments, and theoretical understanding of stellar physics before a star's true nature and scale becomes clear. For Scuti specifically, understanding its true extreme nature required several separate threads of scientific progress to converge. First, astronomers needed reliable methods for determining stellar distances at the scale of thousands of light years. A genuinely difficult problem, since direct geometric parallax measurement, the most reliable distance measuring technique available, becomes increasingly imprecise at greater distances, given that the angular shifts being measured become smaller and smaller, approaching the limits of instrumental precision. Second, astronomers needed a robust theoretical understanding of stellar evolution, specifically the physics governing how stars of different masses evolve, swell, and eventually die, which is itself a body of knowledge that developed substantially throughout the 20th century, incorporating advances in nuclear physics, thermodynamics, and computational modeling of stellar interiors. Third, and specifically for determining Scuti's enormous size, astronomers needed precise measurements of its luminosity and surface temperature, both of which require careful spectroscopic analysis and reliable distance data, since apparent brightness alone tells you nothing about a star's true luminosity without knowing how far away it is. It was only in 2012 that a specific study, drawing on this accumulated body of distance measurement techniques and stellar physics, produced the radius estimate of approximately 1,700 solar radii that brought Scuti significant attention, including in popular science media, as a contender for the title of largest known star. This means that for roughly 152 years between its initial cataloguing and this definitive size estimate, Scuti sat in astronomical catalogues as simply one more variable star among the hundreds of thousands recorded by 19th century survey astronomers, its true nature completely unsuspected. This timeline is worth holding on to because it illustrates something important about how we come to understand extreme objects in the universe. The universe does not announce its most extraordinary features. They sit, quietly recorded as routine data points, until the right combination of technology, theory, and careful analysis reveals what was there all along. Let's talk now about a question that arises naturally from everything we've discussed. Given how rare hypergiants are, and given how briefly they exist in this extreme phase before either exploding or transitioning to some other evolutionary stage, what does it actually mean that we happen to be observing Scuti during this specific, narrow window of its existence? Stellar lifetimes, even for the most massive and fast-evolving stars, are typically measured in millions of years. But the specific hypergiant phase, the period during which a star like Scuti exhibits this combination of extreme size, instability, and rapid mass loss, is thought to represent a particularly brief subset of even that already short total lifetime, possibly lasting only tens of thousands to a few 100,000 years. A tiny sliver of cosmic time. Given that the Milky Way galaxy is roughly 13.6 billion years old and contains hundreds of billions of stars, the probability that any specific massive star happens to be observed during this narrow hypergiant window, at exactly the moment in cosmic history when human astronomers on a small planet around an unremarkable star happen to be looking in the right direction with sufficiently advanced instruments, might seem like an extraordinary coincidence. But this framing somewhat inverts the actual statistical reasoning involved. Across an entire galaxy, at any given moment, there are likely to be at least a small number of stars passing through this hypergiant phase, somewhere among the galaxy's hundreds of billions of stars. Simply because the galaxy is old enough and contains enough massive stars that, statistically, some fraction of them will always be transiting through this brief evolutionary window, even if any individual star only experiences it for a relatively short cosmic instant. We are not catching an impossibly rare one-time event. We are observing one specific example of a phenomenon that, while individually brief, is statistically guaranteed to be occurring somewhere in the galaxy at essentially any given time, given the galaxy's overall population of massive stars. What makes UY Scuti specifically notable is not that hypergiants exist, there are several known examples, but that this particular one happens to be close enough and bright enough and positioned favorably enough relative to obscuring interstellar dust for us to actually measure its properties with reasonable confidence using current instrumentation. There may well be other hypergiants in our galaxy, possibly even larger ones, that remain effectively unmeasurable to us simply due to unfavorable positioning, excessive dust obscuration along our line of sight, or insufficient brightness as observed from Earth. This reframes the entire question of the largest known star in an important way. We are not claiming to have found the single largest star that exists. We are reporting the largest star whose size we have been able to measure with the techniques and instruments currently available to us, fully acknowledging that this measured population represents only a small, possibly unrepresentative sample of the true population of extreme stars actually existing throughout the galaxy and the broader universe. Let's talk about what future observations might reveal, and about the specific technological developments that could meaningfully change our understanding of stellar extremes like UY Scuti in the coming years and decades. The James Webb Space Telescope, which began science operations in 2022, represents a significant advance in infrared observational capability. And infrared observation is particularly valuable for studying objects like hypergiants, because these stars, despite their enormous luminosity, radiate much of their energy at infrared wavelengths due to their relatively cool surface temperatures, and because infrared light penetrates the obscuring interstellar dust that often surrounds these stars far more effectively than visible light. Webb's enhanced sensitivity and resolution offer the potential for more precise measurements of stars like UY Scuti, potentially refining our understanding of its true size, its rate of mass loss, and the structure of the dust and gas it has shed into its surrounding environment. Material that, in cases like VY Canis Majoris, has already revealed surprisingly complex structures of arcs, knots, and loops when studied with sufficient detail, suggesting these stars don't shed material uniformly, but rather through episodic, asymmetric eruptions, whose underlying physical causes remain an active area of research. Beyond Webb, future instruments, including next-generation ground-based telescopes currently in development, such as the Extremely Large Telescope being constructed in Chile with a primary mirror diameter of 39 meters, dramatically larger than any current ground-based optical telescope, promise even greater resolving power, potentially enabling more direct imaging or interferometric measurement of stars like UY Scuti, rather than relying solely on the indirect luminosity temperature method that currently underlies most size estimates for stars at this distance. There's also the ongoing possibility, mentioned earlier, that some currently known star, or some star not yet identified as anything unusual, sitting quietly in an astronomical catalogue, much as UY Scuti once did for over a century, will eventually be revealed through more careful or more advanced measurement to be even larger than UY Scuti. Given the genuine uncertainty in current size estimates for several hypergiant candidates, and given that we have detailed measurements for only an extremely small fraction of the galaxy's total stellar population, this possibility should be considered not merely plausible, but, over a long enough timeline of continued astronomical research, perhaps likely. This is, in a sense, the nature of astronomical knowledge about extremes. The title of largest known star has shifted before, from earlier candidates to VY Canis Majoris to UY Scuti, and there is no particular reason to believe this current ranking represents some final, settled answer, rather than simply our best current understanding, subject to revision as our tools and techniques continue to improve. Let's shift to talk about something that connects this story back to something more directly relevant to us: the relationship between stars like UY Scuti and the actual material that makes up planets and, eventually, living things. Every element heavier than hydrogen and helium, with only trace exceptions produced through other processes, was forged inside the cores of stars through nuclear fusion, or in the explosive deaths of massive stars through supernova nucleosynthesis. This is not metaphor or simplification. It is established physics, confirmed through decades of nuclear astrophysics research, spectroscopic observation of stellar compositions, and analysis of the isotopic ratios found in meteorites and other early solar system material. Massive stars, including hypergiants like UY Scuti, play a particularly significant role in this process because their high mass allows their cores to reach the extreme temperatures and pressures necessary to fuse progressively heavier elements: carbon, oxygen, neon, silicon, culminating in many cases in the catastrophic supernova explosion that not only produces even heavier elements through the explosive nucleosynthesis occurring in the blast itself, but also scatters all of these elements, accumulated over the star's lifetime and forged in the explosion, out into the surrounding interstellar medium. This scattered material, enriched with carbon, oxygen, nitrogen, iron, and a wide range of other elements essential to the formation of rocky planets and to biological chemistry as we understand it, eventually becomes incorporated into the clouds of gas and dust from which future generations of stars and their accompanying planetary systems form. When UY Scuti eventually explodes as a supernova, an event that, as discussed, may have already happened for all we currently know, given the 9,500-year light travel delay, it will release into its surrounding environment a substantial quantity of heavy elements, accumulated through its own internal fusion processes throughout its life, and further synthesized in the explosion itself. This material will eventually disperse through the surrounding region of the galaxy, potentially over the course of tens of thousands to millions of years, gradually mixing with existing interstellar gas and dust. Given enough time, and stellar and galactic processes operate on timescales of millions to billions of years, some portion of this material could conceivably become incorporated into future star-forming regions, eventually contributing to the formation of new stars and new planetary systems, carrying within them atoms that were once part of one of the largest stars known to have existed in our galaxy. This is true, in a general sense, of essentially all heavy elements in the universe, including the elements that make up Earth and every living thing on it. The iron in your blood, the calcium in your bones, the oxygen you breathe, all originally forged inside the cores of stars that lived and died long before our solar system formed, scattered across the galaxy through supernova explosions, eventually gathering together in the cloud of gas and dust that became our Sun and its surrounding planets roughly 4.5 billion years ago. UY Scuti when it eventually meets this fate, will be participating in exactly this same fundamental process, contributing its own forged material to the ongoing cycle through which the universe's stellar and planetary populations are continuously enriched and renewed. Let's talk about the specific physics of what happens when a star like Scuti finally does explode, walking through the actual sequence of events, because understanding this process makes the eventual fate of this star, and stars like it, genuinely vivid rather than abstract. For a hypergiant of Scuti's general mass class, somewhere in the range of 7 to 10 solar masses, though hypergiants with higher initial masses follow somewhat similar underlying physics, the death process is governed by what happens inside the stellar core after all available nuclear fuel has been exhausted through successive fusion stages. Throughout most of a massive star's life, the core fuses hydrogen into helium, generating outward pressure through the energy released that balances the inward pull of gravity, keeping the star in a stable equilibrium. Once core hydrogen is exhausted, the core contracts and heats, eventually reaching temperatures sufficient to fuse helium into carbon and oxygen. This process repeats in stages, with the core contracting and heating each time one fuel source is exhausted, progressing to increasingly heavy elements, carbon fusing into neon and magnesium, neon into oxygen and magnesium, oxygen into silicon and sulfur, and finally silicon fusing into iron. This is where the process fundamentally changes character. Iron is the point at which nuclear fusion stops releasing net energy. Up to iron, fusing lighter elements into heavier ones releases energy, because the resulting nucleus has slightly less mass than the sum of its components, with that mass difference converted into energy according to Einstein's mass-energy equivalence. But fusing iron into anything heavier requires net energy input rather than releasing it. Iron sits at the peak of nuclear binding energy per nucleon, meaning it's the most stable possible atomic nucleus, the endpoint past which fusion can no longer power a star. Once a massive star's core becomes predominantly iron, it can no longer generate the outward pressure needed to resist gravitational collapse. The core, which by this point may be roughly the size of Earth, but containing a mass comparable to the Sun, suddenly and catastrophically collapses under its own gravity, a process that takes mere fractions of a second, with the core's outer regions falling inward at a substantial fraction of the speed of light. This collapse continues until the core reaches densities comparable to an atomic nucleus itself, at which point the strong nuclear force and neutron degeneracy pressure abruptly halt the collapse, causing the core to rebound. This rebound, combined with a colossal burst of neutrinos released during the collapse process, drives a shockwave outward through the remaining layers of the star. This shockwave, as it propagates outward through the star's remaining material, including, for a star like Scuti, that enormous, extended, tenuous outer envelope we discussed, the material reaching out past where Jupiter would orbit, blows the entire outer structure of the star apart in one of the most energetic single events known to occur anywhere in the universe. The resulting explosion, a core collapse supernova, briefly releases an amount of energy that can outshine the combined light of every other star in the host galaxy, visible across enormous cosmic distances. Supernovae have been observed and recorded in galaxies billions of light years away, momentarily appearing as a single point of light, rivaling the brightness of their entire host galaxy of hundreds of billions of stars. For Scuti specifically, given its distance of approximately 9,500 light-years, a supernova explosion would be an extraordinarily bright object as seen from Earth, likely visible during daylight hours, and bright enough at night to cast visible shadows, based on comparisons to historical supernovae observed at somewhat greater distances, such as the supernova of 1006, recorded by astronomers across multiple continents, which was bright enough to read by at night and visible during daytime for weeks. What remains after the explosion depends on the mass of the collapsing core. For a star in UY Scuti's estimated mass range, the most likely outcome is the formation of a neutron star, an object with a mass comparable to the Sun but compressed into a sphere only about 20 kilometers across, with densities so extreme that a single teaspoon of neutron star material would weigh roughly the same as a mountain on Earth. If the collapsing core exceeds a certain mass threshold, generally estimated at somewhere around 2 to 3 solar masses for the remnant core, though the exact boundary remains an active area of research, the collapse continues past the neutron star stage entirely, with gravity overwhelming even neutron degeneracy pressure, resulting instead in the formation of a black hole, an object so dense that not even light can escape its gravitational pull beyond a certain boundary, the event horizon. Given UY Scuti's specific mass estimates, current models suggest a neutron star is the more probable outcome, though given the genuine uncertainty in mass estimates for this star, a black hole outcome cannot be entirely ruled out. Either way, the contrast is worth sitting with directly. A star whose outer surface, while it lived, would have engulfed the orbit of Jupiter, will end its life as an object no larger than a city, 20 kilometers across if it forms a neutron star, or, in the case of a black hole, an object defined by an event horizon that could be smaller still, depending on the final mass involved. From an object larger than the orbit of Jupiter to an object you could drive across in roughly 15 minutes. This is the trajectory that awaits UY Scuti and every other hypergiant of comparable mass class somewhere in its future. A future that may already, unknown to us, have arrived in the 9,500 years since the light we currently observe departed the star. Let's talk now about a related and genuinely fascinating question. What would actually happen to a hypothetical planetary system if one existed around a star like UY Scuti, given everything we've discussed about its size, its mass loss, and its eventual fate? This is necessarily somewhat speculative, since no planets have been confirmed around UY Scuti specifically. Detecting planets around stars at this distance, around a star this unstable and enshrouded in expelled material, presents enormous technical challenges using current detection methods, which generally rely on subtle, regular variations in a star's light or position that would be extraordinarily difficult to discern amid the dramatic, irregular variability already characteristic of a pulsating hypergiant. But we can reason through the physics of what would happen to planets at various distances based on our understanding of UY Scuti's evolution and current properties. Any planet that might have formed at a distance comparable to where Mercury, Venus, Earth or Mars orbit our own Sun would, at this point in UY Scuti's evolution, simply no longer exist as a distinct planetary body. These orbital distances now lie deep within the star's own extended outer envelope, meaning any such planet would have been engulfed entirely as the star expanded into its current hypergiant phase, its material almost certainly incorporated into the star's outer layers, or, depending on the specific dynamics involved, potentially vaporized and dispersed. A planet at a distance comparable to Jupiter's orbit would find itself in an extraordinarily precarious position, right at or just beyond the current outer boundary of the star's visible surface, experiencing intense heating substantial atmospheric stripping from the star's powerful outward-flowing stellar winds, and a generally hostile, rapidly evolving environment as the star continues its mass loss process and potential further expansion. Only planets considerably farther out, at distances comparable to Saturn, Uranus or Neptune in our own solar system, or beyond, might plausibly have survived as intact planetary bodies throughout UY Scuti's expansion into its current hypergiant state, though even these would likely have experienced significant disruption to their original orbits and any atmospheres they once possessed. Given the star's substantial mass loss altering the overall gravitational dynamics of any surrounding system over time, and given the sheer intensity of radiation and stellar wind originating from an object radiating roughly 200,000 times the Sun's luminosity. When UY Scuti eventually does explode as a supernova, any remaining planets, even those that survived the hypergiant phase at safe distances, would face the explosion's shockwave and intense radiation, an event capable of stripping atmospheres, heating surfaces to extreme temperatures, and potentially disrupting orbital stability entirely, particularly given the sudden, dramatic loss of the central star's mass during the explosion, which would fundamentally alter the gravitational binding of any remaining planetary system. This is, in a very real sense, a preview of complications that don't apply to our own Sun, which lacks the mass to become a hypergiant or to end its life in a core collapse supernova. Our Sun's eventual fate, billions of years from now, involves expansion into a red giant substantial enough to engulf Mercury, Venus, and possibly Earth, followed by a much gentler shedding of its outer layers to form a planetary nebula, leaving behind a white dwarf rather than anything resembling the catastrophic, planet-annihilating violence that awaits a true hypergiant like UY Scuti. Let's pause here on something that connects directly back to where we started this whole journey, and consider it from a slightly different angle. We began by establishing the size of our own Sun and the scale of our solar system relative to it. We then built, piece by piece, toward UY Scuti, a star so large that if it replaced our Sun, every planet out to and including Jupiter would exist inside its own outer atmosphere. But there's an important asymmetry worth highlighting explicitly. Our Sun, despite being almost laughably modest in size compared to UY Scuti, is in many respects the more fortunate star to be associated with, at least from the perspective of anything living nearby. Our Sun is stable, in a way UY Scuti fundamentally is not. It has burned steadily, with only gradual changes in luminosity, for roughly 4.5 billion years, and is expected to continue doing so in a relatively stable fashion for several billion more. A timeline that has allowed, on at least one planet within its system, billions of years of relatively undisturbed conditions sufficient for complex life to emerge, diversify, and eventually develop the capacity for the kind of careful astronomical measurement that allows us to understand objects like UY Scuti from 9,500 light-years away in the first place. UY Scuti, by contrast, exists in a state of dramatic instability, pulsating, shedding mass at an extraordinary rate, radiating energy at a level that would be utterly inhospitable to anything resembling life as we understand it anywhere within a vast surrounding region, and facing an essentially inevitable, cataclysmic, explosive end within what is, on stellar timescales, a remarkably short remaining lifespan. The very property that makes UY Scuti spectacular and worth dedicating an hour of careful explanation to, its almost incomprehensible physical size, is also intimately connected to the instability and violence that defines its existence. Stars don't become this large by being calm, stable, long-lived objects. They become this large specifically because they are massive stars rapidly approaching the end of relatively short lives, undergoing dramatic internal restructuring as they exhaust progressively heavier nuclear fuels in their cores, with their enormous size being, in a very real physical sense, a direct symptom of this approaching stellar death, rather than something separate from it. This is, in its own way, a kind of cosmic trade-off worth sitting with. The universe's most visually and physically extreme stellar objects tend to be, almost by definition, its most short-lived and unstable ones. The steady, modest, billions of years stable stars like our own Sun, the kind of star around which the patient, gradual processes of planetary formation and biological evolution actually have time to unfold, are, by comparison, almost unremarkable in terms of raw physical scale. We happen to live around one of the unremarkable ones, and that, in this specific and very real sense, may be precisely why we exist at all, to look outward and measure the remarkable ones. Approaching from a great distance, Scuti would initially appear as nothing more than an unusually bright point of reddish-orange light, distinguishable from an ordinary star primarily by its colour, that deep red-orange hue, characteristic of red hypergiants, resulting from its relatively cool surface temperature of roughly 3000 to 3600 Kelvin, compared to our Sun's much hotter, yellower white 5800 Kelvin surface. As you drew closer, and we're talking about distances that would still represent enormous spans even in interplanetary terms, the star would begin to noticeably grow in apparent size, eventually transitioning from a point of light to a visible disk, and then, as you continued approaching, the disk would begin to dominate an increasingly large portion of your field of view. Unlike our Sun, whose visible surface is relatively sharply defined, the photosphere transitioning to the much fainter, only occasionally visible corona over a relatively short distance, Scuti's outer boundary would likely appear considerably more diffuse and gradual, a consequence of its tenuous, extended outer atmosphere lacking the sharp density gradient of a more compact star. You would likely pass through increasingly dense wisps and layers of stellar material well before reaching anything resembling a clearly defined surface, with the boundary between approaching the star and being inside the star's outer atmosphere becoming genuinely ambiguous rather than sharply demarcated. The light itself, despite the star's staggering total luminosity, that 200,000 or so times solar output we calculated earlier, would actually appear notably dimmer and redder per unit area compared to the surface of our own Sun, precisely because that enormous total energy output is being spread across such an enormous surface area. The intensity of light at the surface of a star is actually a function of temperature alone, not total luminosity. And given Scuti's relatively cool surface temperature compared to the Sun, the light emanating from any given patch of its surface would be considerably less intense and considerably redder in colour than equivalent light from the Sun's surface, even though, integrated across the star's entire enormous surface area, the total energy output is vastly greater. This is a genuinely counterintuitive aspect of stellar physics worth dwelling on. Standing at the surface of Scuti, despite being inside one of the most luminous objects known in the universe, the immediate visual experience, purely in terms of the brightness and colour of light coming from the material directly around you, would actually be somewhat dimmer and more deeply red than standing at the surface of our comparatively modest Sun, simply because that staggering total energy output is diluted across such an extraordinarily vast surface. What would be inescapable, however, is the sheer scale of everything around you. Looking in any direction along what would functionally be the star's curved surface, you would see this reddish, glowing material extending outward for distances comparable to the radius of our entire solar system, out to Jupiter. A horizon, if such a concept even meaningfully applies in this tenuous, gradually fading stellar atmosphere, that would be almost impossible to perceive as curving away from you in any practically noticeable sense, given that the star's radius, at roughly 1,700 times that of the Sun, is so vastly larger than any scale at which human perception of curvature would typically register. Looking outward, away from the star, you would be looking out across a distance comparable to the entire orbit of Jupiter before reaching anything resembling truly empty interstellar space. Meaning that from a position at or near UY Scuti's surface, the entirety of what would be, around our own Sun, the orbits of Mercury, Venus, Earth, Mars, the asteroid belt and Jupiter would all be encompassed within the star's own stellar material, with genuinely empty space beginning only at distances comparable to where Jupiter currently orbits the Sun. Let's talk now about something more directly tied to observational astronomy and what's actually visible from Earth, because there's a particular nuance worth addressing, given everything we've discussed about UY Scuti's staggering scale and energy output. Why isn't it one of the brightest objects in our night sky, rather than a star requiring a telescope to observe at all? The answer lies entirely in distance, and it's worth working through the actual physics involved because it powerfully illustrates just how the inverse square law governing light intensity over distance can overwhelm even truly staggering intrinsic luminosity. The apparent brightness of any light source, as observed from a given distance, decreases with the square of that distance, meaning that if you double the distance to a light source, it appears only 1/4 as bright. Triple the distance, and it appears only 1/9 as bright, and so on. UY Scuti sits at a distance of approximately 9,500 light-years from Earth. For comparison, the vast majority of stars visible to the naked eye in Earth's night sky lie within a few hundred light-years of us, meaning UY Scuti is typically tens to potentially over 100 times more distant than most of the named, easily visible stars populating typical constellations. Given the inverse square relationship, being even 10 times more distant than a comparison star reduces apparent brightness by a factor of 100. Being 100 times more distant reduces apparent brightness by a factor of 10,000. UY Scuti's luminosity, at roughly 200,000 times that of the Sun, is genuinely enormous compared to most other stars. But it is not enormous enough to fully overcome a distance penalty of this scale. The result is that UY Scuti, despite being one of the most luminous and certainly one of the largest stars known to exist in our entire galaxy, has an apparent magnitude, as observed from Earth, of only around magnitude 9 to 11, depending on its variable brightness at any given time. Far too dim to be seen with the naked eye, which typically can detect stars down to roughly magnitude 6 under excellent dark sky conditions, and requiring at minimum a moderately capable amateur telescope to observe directly at all. This is worth sitting with as a final point about scale. An object genuinely large enough to swallow the orbit of Jupiter, radiating roughly 200,000 times the energy output of our Sun every single second, is rendered by the simple mathematics of distance into something requiring specialized equipment merely to detect as a faint point of light, utterly indistinguishable to the unaided human eye from any number of far smaller, far less remarkable stars scattered across the same patch of sky. The universe's most extreme objects are not necessarily its most visually obvious ones from our particular vantage point on a small planet orbiting a modest star. Scale and brightness, while related, are mediated by distance in ways that can render even the most extraordinary objects functionally invisible without the right instruments and the right knowledge of exactly where and how to look. Let's talk about something that ties several threads of this discussion together: the question of what it would mean, practically and scientifically, if humanity were ever to develop the technology to send some kind of probe or observational instrument significantly closer to Scuti. Even setting aside the obvious and essentially insurmountable challenges of distance and travel time involved in any such hypothetical mission. At 9,500 light-years, even a hypothetical spacecraft travelling at a significant fraction of the speed of light, say 10% of light speed, a figure already far beyond any propulsion technology currently available or seriously proposed for near-term development, would require 95,000 years simply to complete the one-way journey. A timescale that dwarfs the entirety of recorded human history many times over, and that raises immediate and serious questions about the practical feasibility of any such endeavour, even leaving aside whether a spacecraft, or any human-built system, could realistically be expected to function reliably across such an immense span of time. This is, in a very real sense, the practical barrier that separates astronomy from genuine exploration when it comes to objects at truly interstellar and certainly at this kind of galactic distance. We can observe Scuti in remarkable detail using light that has travelled across the intervening 9,500 light-years on our behalf, requiring no propulsion technology of our own beyond the construction of sufficiently sensitive telescopes here on or near Earth. But direct physical exploration, sending instruments or, far more distantly conceivable, any kind of crewed mission to actually visit and study the star directly at close range, remains, with any currently foreseeable technology, entirely outside the realm of practical possibility. This distinction matters because it shapes the fundamental nature of what we can know about an object like Scuti. Everything we've discussed throughout this entire exploration, its size, its mass, its luminosity, its temperature, its rate of mass loss, its likely future evolution and eventual explosive death, all of this knowledge derives entirely from analysing light that has travelled undisturbed across thousands of years and thousands of light-years of largely empty interstellar space, captured by telescopes and analysed through the careful, accumulated theoretical framework of stellar physics developed by generations of astronomers and physicists. We have never touched this star in any sense. We have never sent anything to it, and almost certainly never will, given any currently foreseeable technological trajectory. Everything we know about one of the largest physical objects in our entire galaxy comes exclusively from patient, careful analysis of light. Photons that left the star's surface roughly 9,500 years ago, crossed the vast emptiness of interstellar space, largely undisturbed, and eventually arrived at telescopes built by a species that, for the overwhelming majority of that 9,500-year journey, didn't yet exist in anything resembling its current form, hadn't yet developed writing, agriculture, or any of the foundational technologies that would eventually lead to the construction of telescopes and the development of the physics necessary to interpret what those telescopes revealed. This is, in its own way, one of the more remarkable aspects of the entire story we've been telling tonight. Not simply the staggering physical scale of Scuti itself, impressive as that scale undeniably is, but the fact that creatures on a small, rocky planet, orbiting an unremarkable star, using nothing but careful analysis of ancient starlight and several centuries of patiently accumulated physics and astronomy, have managed to determine, with reasonable scientific confidence, the size, mass, temperature, luminosity, likely future, and probable eventual fate of an object so distant that the light currently reaching us left its surface before the invention of writing, before the founding of any civilization whose records survive to the present day, during an era when human beings across the planet were only beginning the long, slow transition from nomadic hunting and gathering towards settled agricultural life. We have, in a very real sense, learned the future of an object whose present state we cannot actually observe and have no immediate way of ever directly confirming. Reasoning forward from established stellar physics to predict that this star, sometime in a window that could span anywhere from the present moment to perhaps a few 100,000 years from now, will undergo a catastrophic explosive death, will briefly become one of the brightest single objects visible from Earth, and will ultimately leave behind either a neutron star or a black hole, scattering newly forged heavy elements into the surrounding galaxy to eventually become incorporated into future generations of stars and planets. Whether that explosion happened 5,000 years ago, or will happen 5,000 years from now, or any time across the considerably wider range of genuine astronomical uncertainty involved, is something we currently have absolutely no way of knowing with any certainty, and may not know for certain until the light from that eventual explosion, whenever it occurred or occurs, finally completes its own 9,500-year journey across the emptiness separating UY Scuti from Earth, arriving here to be observed by whatever form human civilization, or its descendants, or its instruments happen to exist at that future moment to receive it. Let's take a step back and talk about the broader category of objects that astronomers refer to when discussing extreme stellar sizes. Because UY Scuti exists within a taxonomy of stellar classification that's worth understanding properly, rather than treating biggest star as a single, isolated curiosity disconnected from the broader framework of how astronomers actually categorize and think about stars. The Hertzsprung-Russell diagram, developed independently in the early 20th century by Danish astronomer Einar Hertzsprung and American astronomer Henry Norris Russell, remains the foundational tool astronomers use to organize and understand the relationships between different types of stars. The diagram plots stellar luminosity against surface temperature, and when you place enough stars onto this kind of chart, clear patterns and groupings emerge that correspond to genuinely distinct evolutionary stages and physical categories of stars. Most stars, for most of their lives, occupy what's called the main sequence, a diagonal band running from hot, luminous blue-white stars in the upper left of the diagram down to cool, dim red stars in the lower right. Our Sun sits roughly in the middle of this band, a fairly unremarkable yellow dwarf star currently in the hydrogen fusing phase that constitutes the majority of any star's total lifetime. Stars leave the main sequence once they exhaust the hydrogen fuel in their cores, and the direction and extent of their subsequent evolution depends almost entirely on their initial mass. Lower mass stars, like our Sun, evolve into red giants, significantly larger and cooler than their main sequence selves, but nowhere near the scale of true hypergiants, before eventually shedding their outer layers and settling into a compact white dwarf remnant. Higher mass stars, generally those beginning their lives with at least 8 to 10 times the mass of the Sun, follow a substantially different and considerably more dramatic evolutionary path. These stars evolve into supergiants, and the most massive among them into hypergiants, occupying the uppermost regions of the Hertzsprung-Russell diagram, characterized by extreme luminosity combined with, in the case of red supergiants and red hypergiants specifically, relatively cool surface temperatures that, as we discussed earlier, mathematically necessitate enormous physical radii to account for their tremendous total energy output. It's worth noting that not all supergiants and hypergiants are red. Blue supergiants and blue hypergiants also exist, representing stars with similarly extreme luminosities, but much higher surface temperatures, generally tens of thousands of Kelvin, rather than the few thousand Kelvin characteristic of red hypergiants like UY Scuti. Because temperature and radius trade off against each other in determining total luminosity, blue hypergiants, despite their extreme total energy output, tend to have considerably smaller physical radii than red hypergiants of comparable luminosity, meaning the title of physically largest star specifically favors the red, cooler end of the hypergiant spectrum, which is precisely why UY Scuti, VY Canis Majoris, and similar red hypergiants dominate discussions of stellar size specifically, even though other stars exist with comparable or even greater total luminosity, while being considerably more compact. This distinction matters because it clarifies exactly what kind of biggest we're discussing throughout this entire exploration. We have been talking specifically about physical radius, the literal spatial extent of these stars, rather than mass, rather than total luminosity, rather than any other measure by which one might rank stellar extremes. By the measure of mass, far more massive stars exist than UY Scuti, some with initial masses estimated at over 100 times that of the Sun, though these extremely massive stars tend to be hot, blue, and physically far more compact than the cooler red hypergiants that dominate the size rankings. The most massive stars currently known, by contrast to the largest by physical radius, include objects like R136A1, located in the Large Magellanic Cloud, with mass estimates in some studies exceeding 150 to even potentially over 200 times the mass of the Sun, making it one of, if not the, most massive star currently known to astronomers. Yet R136A1, despite this staggering mass, has a radius estimated at only around 30 to 40 times that of the Sun, physically far smaller than UY Scuti, despite containing vastly more total material. Precisely because R136A1 is an extremely hot blue star, with a correspondingly compact radius required to produce its enormous luminosity at that much higher surface temperature. This contrast is worth sitting with directly. UY Scuti, with an estimated mass of merely 7 to 10 solar masses, has a radius roughly 40 to 50 times larger than R136A1, despite R136A1 containing somewhere between 15 and 20 times more total mass. Physical size and mass, as we touched on earlier when discussing UY Scuti's remarkably low average density, are simply not the same property, and a star's position in its specific evolutionary journey, whether it's a young, hot, compact, extremely massive blue star, or an older, cooler, extraordinarily extended red hypergiant nearing the end of its life, determines its physical radius in ways that can completely decouple from its total mass. Let's talk now about something that connects this stellar taxonomy back to deeper questions about why the universe produces objects across such an extraordinary range of scales and properties in the first place. Specifically, why stellar masses themselves span such an enormous range, from the smallest possible stars to the most massive ones we've discussed. The minimum mass required for an object to become a true star, meaning an object capable of sustaining stable hydrogen fusion in its core, sits at approximately 0.08 times the mass of the Sun, or roughly 80 times the mass of Jupiter. Below this threshold, an object simply cannot generate sufficient core temperature and pressure to ignite and sustain hydrogen fusion, instead becoming what's known as a brown dwarf, an object intermediate in nature between the largest gas giant planets and the smallest true stars, capable of some limited fusion of deuterium,
a heavier isotope of hydrogen, but never achieving the stable, sustained hydrogen fusion that defines true stellar status.
At the upper end of stellar mass, the theoretical limit is considerably less precisely established, though current understanding suggests stars exceeding roughly 150 to potentially 300 times the mass of the Sun may be physically possible, though exceedingly rare, with their formation and stability constrained by complex interactions between gravitational collapse during star formation and the radiation pressure generated by the resulting extremely luminous massive star, which can become strong enough to halt further mass accretion or even potentially disrupt the forming star entirely. This means that across the entire observed and theoretically permitted range of stellar masses, we're looking at a span from roughly 0.08 solar masses at the very low end to perhaps 150 to 300 solar masses at the extreme high end, a factor of somewhere between roughly 2,000 to 4,000 across the full range of stellar mass that the universe appears capable of producing and sustaining. This vast range exists because of the specific physics governing gravitational collapse and nuclear fusion ignition during star formation. Stars form when sufficiently large clouds of interstellar gas and dust, primarily hydrogen, begin to gravitationally collapse under their own weight, with the exact mass of the resulting star determined by the amount of material available within the collapsing region, the specific dynamics of that collapse process, and a range of other factors, including the cloud's initial density, temperature, and any external influences, like nearby massive stars, whose radiation and stellar winds can either trigger or disrupt nearby star formation. The resulting distribution of stellar masses, when you survey large populations of newly formed stars across various star-forming regions throughout the galaxy, follows a well-characterized statistical pattern known as the initial mass function, first described in detail by astronomer Edwin Salpeter in 1955 and refined considerably by subsequent research. This distribution reveals that low-mass stars form in dramatically greater numbers than high-mass stars, meaning that for every star as massive as UY Scuti's progenitor likely was, or certainly for every star approaching the mass of objects like R136A1, vastly larger numbers of smaller, Sun-like or even smaller red dwarf stars form throughout the galaxy. This statistical pattern is part of why true hypergiants like UY Scuti are so genuinely rare, and why finding and studying them represents such a valuable opportunity for understanding the most extreme end of stellar physics. They represent a relatively small, short-lived, and increasingly well-studied, but still incompletely understood, tail end of the overall stellar population, vastly outnumbered by the more common, longer-lived, smaller stars that constitute the overwhelming majority of any galaxy's total stellar census. Let's talk now about something that brings this entire discussion back toward a more reflective register, specifically about what the existence of objects like UY Scuti reveals about the nature of physical law itself, and about the relationship between the equations governing stellar physics and the genuinely staggering, almost unbelievable physical outcomes those equations can produce when applied across sufficiently extreme conditions. The physics governing UY Scuti's existence, the relationship between mass, fusion rate, luminosity, temperature, and radius that we've discussed throughout this exploration, is fundamentally the exact same physics that governs our own Sun, the same physics that governs every other star in the observable universe. There is no separate or special category of physical law that applies uniquely to hypergiants. The Stefan Boltzmann law, relating luminosity to temperature and surface area, the nuclear physics governing fusion reaction rates and energy release, the basic principles of hydrostatic equilibrium balancing gravitational compression against internal pressure. All of these are universal physical relationships, applicable identically whether you're calculating the properties of our modest, stable, main sequence Sun, or the properties of an extraordinarily extended, unstable, late-stage hypergiant like Scuti. What differs between these two cases is not the underlying physical law, but rather the specific initial conditions, primarily mass, and to some extent the precise evolutionary stage, fed into those same universal equations. A star beginning its life with roughly the Sun's mass, following these same physical laws across billions of years of relatively stable hydrogen fusion, produces the kind of steady, modest star capable of supporting, on at least one orbiting planet, the multi-billion-year stability necessary for complex life to emerge and evolve. A star beginning its life with somewhat greater mass, though, as we discussed, Scuti's progenitor was likely not even extraordinarily massive by the standards of the most massive known stars, following these exact same physical laws, but across a different evolutionary trajectory, involving the exhaustion of core hydrogen and the subsequent dramatic restructuring of the star's internal physics during successive fusion stages, can produce an object whose physical radius, derived from nothing more exotic than the same Stefan Boltzmann relationship governing every other star's size, happens to work out to roughly 1,700 times that of the Sun, large enough to swallow the orbit of Jupiter. There is something worth genuinely appreciating in this fact. The same handful of relatively simple physical relationships, when applied consistently and rigorously across the full range of conditions the universe actually produces, naturally and inevitably generate outcomes spanning from the comfortable, life-supporting stability of stars like our Sun to the almost unbelievable physical extremity of objects like Scuti, without requiring any additional or special physical principles beyond the same basic stellar physics applicable everywhere. This is in many ways one of the more remarkable aspects of how physical law actually operates throughout the universe. Not that different categories of objects require fundamentally different rules, but that a relatively compact, well understood, mathematically precise set of physical relationships, when applied across the genuinely vast range of initial conditions the universe provides, naturally produces an equally vast range of resulting physical outcomes, from the smallest brown dwarfs barely failing to achieve true stellar fusion, to the most massive blue supergiants pushing the theoretical upper limits of stellar mass, to the most physically extended red hypergiants like Scuti, whose enormous radius emerges not from any special or exotic physics, but simply from the same equations that describe every other star, applied to the specific combination of luminosity and temperature that happens to characterize this particular late-stage evolutionary moment in this particular star's life. Let's bring this back finally to a more direct and personal register, because I think after this much detail, this much physics, this much careful unpacking of scale and distance and stellar evolution, it's worth simply sitting with the core fact one more time, stripped of further elaboration. There is a star, located roughly 9,500 light years from where you currently are, whose physical surface, were it to somehow replace our own Sun, would extend out past the orbit of Jupiter, encompassing within its own stellar material the entire space currently occupied by Mercury, Venus, Earth, Mars, the asteroid belt, and Jupiter itself. This star is real. It has been measured, studied, and documented through generations of accumulated astronomical technique, beginning with its unremarkable cataloguing in 1860 as simply one more variable star among hundreds of thousands, and culminating, over a century and a half later, in our current understanding of it as one of, if not the, largest physical objects of any kind currently known to exist anywhere in the observable universe. It is, despite this staggering physical scale, profoundly unstable, shedding mass continuously, pulsating irregularly, radiating roughly 200,000 times the energy output of our own Sun from a surface that, due to its enormous extent, actually appears dimmer and redder per unit area than our Sun's own much smaller, much hotter surface. It is approaching, on a timescale that could be tomorrow or could be hundreds of thousands of years from now, a catastrophic explosive death. A death that, given the 9,500-year delay required for light to travel from the star to Earth, may have already occurred without our knowledge, the evidence of that explosion currently somewhere in transit across the vast emptiness of interstellar space, en route to eventually illuminate Earth's night sky with a brightness that historical records of comparable past supernovae suggest could rival or exceed the brightness of the full moon, visible during daylight hours for a period of weeks to months before gradually fading. And all of this, every detail we've discussed tonight, the size, the mass, the temperature, the luminosity, the instability, the eventual fate, emerges from nothing more exotic than the same basic physical laws governing every other star in the universe, including the comparatively modest, stable star currently providing the light and warmth that at this very moment makes possible whatever planet or surface you happen to be standing on as you consider all of this. Let's close out this particular thread by talking about something that ties the entire night together. What this story actually leaves us with intellectually once all the numbers settle. We started with the Sun, something familiar, something whose scale, while large, is at least graspable through the everyday experience of feeling its warmth on your skin. From there, we moved outward in careful, deliberate steps. Betelgeuse, large enough to reach Mars. VY Canis Majoris, large enough to approach Saturn. And finally, UY Scuti, large enough to swallow Jupiter's orbit whole, a star whose discovery as something extraordinary took a century and a half to unfold from a routine, unremarkable catalogue entry. What's worth holding on to isn't simply the number itself, 1,700 solar radii, 2.4 billion kilometers in diameter, a volume that could contain billions of suns. Numbers like that, stretched far enough beyond ordinary experience, tend to blur into abstraction no matter how many comparisons we use to anchor them. What's worth holding on to is the method. The fact that a species standing on a small rocky planet around an unremarkable star, using nothing but patient observation of ancient light and several centuries of carefully accumulated physics, managed to determine the size, mass, temperature, and probable fate of an object so distant that its light left before the invention of writing. That is, in its own way, just as remarkable as the star itself. The universe contains UY Scuti, whether or not anyone is watching. But the fact that someone is watching, that the measurement exists at all, that the number 1,700 solar radii sits in scientific literature rather than simply being an unknown property of an unremarkable point of light in a 19th century star catalogue, that part required us. Somewhere out there, 9,500 years in the past, a star was already swelling toward the edge of its own existence. And somewhere here, considerably more recently, a species figured out how to read that fact in starlight. Go outside tonight and look toward the constellation Scutum, low in the southern sky if you're in the northern hemisphere, near the tail of Aquila the eagle. You won't see UY Scuti. It's far too faint, too distant, requiring a telescope just to register as a point of light. But you'll be looking in its direction. Somewhere in that patch of sky, 9,500 light-years away, sits an object whose surface, if it replaced our Sun, would extend past the orbit of Jupiter. Here is what that actually means, one more time, stripped down to its essentials. Our Sun has a radius of about 696,000 kilometers. UY Scuti's radius, by the estimate that made it famous, is roughly 1,700 times that, about 1.2 billion kilometers, making its diameter approximately 2.4 billion kilometers. Mercury, Venus, Earth, Mars, the entire asteroid belt, and Jupiter would all exist inside that volume, not orbiting it, inside it. And yet this star, despite its almost incomprehensible size, has a mass of only 7 to 10 times the Sun's, making it so diffuse that its average density is roughly 1,000 times less than the air you're breathing right now. Size and mass in stars like this come apart completely. A star can be enormous and almost weightless by comparison, all because of where it sits in its own evolutionary story. A massive star in the final, swollen, unstable stage, before its core runs out of fuel it can burn. That instability is the whole point. UY Scuti is not large because it is calm and enduring like our Sun. It is large specifically because it is dying, spreading its tremendous energy output, some 200,000 times the Sun's luminosity, across a surface so vast that the light per square meter is actually dimmer and redder than our own Sun's. It is shedding mass continuously, wrapped in nebulae of its own expelled material, counting down, on a timescale that could be tomorrow, or could be a few 100,000 years from now, to a supernova that will briefly outshine its entire galaxy as seen from far away, and will likely be visible from Earth in daylight. Whether that has already happened, we cannot know. The light reaching us left UY Scuti around 7,500 BCE, before writing, before agriculture as we know it in most of the world, before any civilization whose name survives. Whatever the star is doing right now, in real time, we won't know for another 9,500 years. And even this, even the title largest known star, is provisional. We have only measured a tiny fraction of the few 100 billion stars in our own galaxy, let alone the 2 trillion galaxies beyond it. Somewhere out there, almost certainly, something larger exists, simply unmeasured, sitting quietly in a catalogue, the way UY Scuti itself sat for over a century before anyone understood what it was. That, maybe, is the real point of tonight, not the number. The fact that the number was found at all, that careful, patient attention applied across generations, turned an unremarkable dot in an 1860 survey into one of the most staggering physical facts we know about the universe. Somewhere out there, a star larger than our entire inner solar system is quietly burning out. And somewhere here, you now know its name.